Okay, very happy to have Roger Melko today for the Quantum BC seminar. Roger holds PhD from UC Santa Barbara and is a professor at University of Waterloo and Perimeter Institute. Also has affiliations with Vector and Creative Destruction Lab, and he's a highly decorated and well-recognized researcher, and many of us are very happy to be collaborators and colleagues with him. Roger is a student of all things quantum, focusing on many-body system, quantum information, with emphasis on computational methods, including machine learning and theoretical techniques. So, Roger, please take it away.
Amazing. Thanks so much, Tech. I forgot to press play here. Hopefully that still comes through. Thanks for the introduction, and you're too kind to me. Thanks for the invitation to give this talk. It's great to be. I'm trying out some new material on you guys, so happy to take any feedback because the topic's a little bit different than what I usually would give in a kind of purely scientific seminar. I want to talk about open quantum design, which is a new initiative from the University of Waterloo, where I'm a professor, as Tech mentioned. Perimeter Institute, where I spend 50% of my time in principle, and Institute for Quantum Computing on campus at Waterloo, where I'm an affiliate, and which is has both an experimental and a theoretical effort in quantum computing, as you know. So the device on the right-hand side there is one of, or I would say IQC's, one of their main efforts towards building a quantum computer, which is an ion trap device. Importantly, for this talk, the intellectual property policies of all of these three institutions are 100% creator owned. So I'll come back to that, but in the sense that we, the principal investigators and our students, and you can see a bunch of them at the bottom of this slide, own the intellectual property that we put into devices and experiments and theory surrounding the devices and control infrastructure such as this. So I'm going to talk about how open quantum design kind of came about as maybe sort of a philosophical endeavor and an institutional organization, and a little bit about my story about how I got involved, and hopefully I can get all of you out there on the West Coast also interested in joining. So please interrupt with questions. I kind of roughly have an outline that I thought I would get to. Hopefully my slide just advanced. I want to talk a little bit about what an open source foundation is, and maybe why, what incentivizes it for quantum computing. Then I want to talk about our trapped ion quantum computer. Oh, trapped ion, but trapped ion. The current state of that system, and some of technology that lives within the organization OQD itself. So I'm going to start with just kind of a sort of broad philosophy about open source foundations, the model, and why they're applicable to quantum computing. So, as Wojtek mentioned, I've been I'm the scientific director of CDL Quantum, which is a startup incubator for quantum startups that launched in 2017 out of University of Toronto Rotman Business School. Xanadu was the first startup that went through CDL's program. Xanadu's success, in some sense, incentivized the launch of this stream, which this is actually this slide's about a year old, but we've helped 140 or more. I would probably say 100 and we're probably well over 160, getting closer to 180 ventures now. Basically receive mentorship is what CDL in some sense does. They've raised a huge amount of capital. I'm sure that's well over 800 million now. And at some point, a fifth of quantum startups on Earth had gone through our program. I think our share of that is dwindling a bit as more and more of these incubators come along. Point with CDL is I learned a lot about how organizations that try to either build quantum full stack computers or components for devices or QKD systems or quantum sensing plays are sort of structured and incentivized and so on. And it led some of us to think about, what's the pain point in organizations? What is, generally the thing that we're trying to solve as we incubate these startups, which are typical venture-backed startups. So, the venture capitalists expect a large kind of scaling of companies typically. So achieving scale is my answer to that. We all know about Moore's law and achieving scale in conventional computing. I would argue we're going through another revolution in scaling in LLMs. These famous scaling laws for large language models came out in 2020, which showed that if you're not bottlenecked by compute parameters or data, then you can keep scaling these things indefinitely, of course, up to economic considerations. And so I think really in some sense what we're trying to achieve with quantum computing is another scaling breakthrough in that sense. And as scientists, I think we typically focus on the engineering and scientific challenges. And I think as professors and educators, we know a lot about the talent issue behind this. And there's also, I'd say, a third pillar, which is the economics issues. Of course, we have computers today because of semiconductor foundries and fabs. And, there's something like $100 billion a year goes into new capital expenditures for these fabs. 100 billion US or more, maybe 200 billion. So there is a lot of investment in conventional computing technology, silicon technology, because there's proper, I would say, economic incentives. And so I think as part of this exercise of working at CDL and looking at quantum computing startups especially, I also started to think about the incentive structures and the organizations and the institutions that go into this kind of quest for scale. And so just to mention about the current institutions that many of us are part of as we try to think about quantum technology and think about scaling quantum technology. Of course, academia, education, research and academia, we're largely all familiar with, I assume. And of course, government, we receive government funding. Government funds a lot of quantum computing development. In other countries, these are now considered, sovereign national interests in many countries. And then SMEs or startups and large caps, I think are the other two institutions we're familiar with. Of course, large cap, I mean something like Microsoft, Google, AWS, right? Building quantum computing divisions internally. I was at Santa Barbara when Microsoft Station Q first launched. It would have been 2000, so it was 20 years ago. Microsoft Station Q came out and started hiring postdocs, and they were trailing D-Wave by about 5 years, probably. D-Wave launched just roughly 25 years ago. So, I think Microsoft was the first large cap company to really get into this. I just put up some pros and cons, and I think we live these every day. One thing is a technical point, which I thought about a lot, and the incentive structure around for-profits and whether or not these give us the best technical designs, and this is completely debatable. If you believe in the free hand of the market, then in some sense, I think for-profit incentives will give you a machine that I guess addresses the market in question. But I think you could also ask whether we see the best design choices technically in this writ large. So part of my pitch to you guys, is another nonprofit structure that I'll talk about next. Proprietary and for-profit go hand in hand. So hardware is increasingly becoming proprietary, even to the point, and I made it the point here, up to the error models. So different pieces of hardware give different error, different hardware plays of different error models, which used to be published quite openly, and I believe are, I would argue, increasingly becoming proprietary, which makes it difficult for outside engineers to really build control systems that take those into account. And a proprietary stack, of course, makes that, I would maybe call that part of benchmarking, but also regulation much more difficult. And also as scientists, we all know when you want to collaborate with a company with interesting hardware, we're immediately presented with an NDA. And what I would call that is a sort of friction, a collaboration friction. I mean, they do have their place, and of course, there is an argument for proprietary technology. But there's a strong, I would argue, a strong culture of NDAs amongst quantum computing. So are there other models possible? And that's what I'm here to talk about today. I see a question on chat, but I can't see the question. Is there a question? I guess I have to click on it. Oh, no.
That was just me, Roger. So yeah.
Actually, I do have a question.
Here we go.
Would you say this NDA culture in quantum is a bit aggressive, or this is just standard, like in academia to industry?
I don't know another world very well.
I see.
So it seems strong to me, but I think it's because, you know, it seems strong because quantum computing is at a sort of more nascent stage of technological development than other things, right? If I walk into Western Digital, I'm presented with an NDA and it makes a lot of sense.
Yeah.
Right? Because they have technology in that building that they don't want me talking about right? But here, I think it's because of the proximity to academic research, the fact that there's still great gains being made academically, and you know, and any quantum connoisseur will tell you, like, we haven't even settled on the qubit, right?
Right.
So we're so close to academia, and we're spinning startups out, that I think that's why it seems that the NDA culture is very aggressive.
I see. Thank you.
I'm going to keep going, but just interrupt if there's more questions. So my proposal, my pitch, is an open source foundation, which is, for some of us, a familiar model. For some of us, maybe we've never seen it before, but it's a nonprofit membership-based model that I think has a very strong foundation in things like Linux, Mozilla, and other, I guess you would call them, Silicon Valley organizations. So Open Quantum Design is modeled very much after a Linux Foundation model, and Linux Foundation is a foundation of foundations. It's kind of confusing. I don't mean the actual Linux kernel, but you may be familiar with open source foundations. Anyone who's fooling around with AI right now and using PyTorch. PyTorch is developed in a foundation very similar to what I'm going to talk about. And so that's an easy entry point. If you look at PyTorch Foundation, just Google it, look at how they're structured. PyTorch used to be developed by Meta, right? And so what Meta did is offloaded PyTorch into this foundation. And now if you look at the membership list, it's Meta, but it's a whole bunch of other people, NVIDIA, Microsoft, I'm just guessing. But all of the competitors in principle get together under the umbrella of the PyTorch Foundation, and they develop the standard and the kernel themselves together, right, in an open source way. So it's an existing model of collaboration, which is actually very well used, I'd say, in the technology sector. RISC-V is the other example, which I won't talk too much about, but RISC-V is an open source ISA that came out of Berkeley. It was launched out of Berkeley, and contains the instruction set architecture and all sorts of amazing things like the root of trust protocols, that allow you to build your own silicon. So I don't know what you do. I've never done it, but if you've done computer engineering, you're certainly familiar with RISC-V. You essentially design your own chips, send that design to a fab. It's printed out. So an open source quantum computer is one which, along this spirit, I would say, is where we open source the hardware, firmware, designs of the hardware, the standards, the procedures by which the thing's assembled, all of the codes that underlie everything in the stack, freely under some license, but freely, and we can talk about licenses, which allow it to be redistributed and modified. That's kind of a standard open source, I think, definition. And I would argue, you could imagine there's all sorts of open source stuff going on in quantum computing, but in particular, I think what makes something like RISC-V special is the idea that design information is released in a way that should allow you to manufacture. In RISC-V, it's the case of the chip, but in our case, we really want you to manufacture the computer itself. Okay, so that was my intro. Oh, there, I fixed my typo. That was my intro to the foundation. I want to get back to it. So that was just a teaser. But I do want to talk a little bit about our particular computer, which is a trapped ion device. So maybe any more questions on that first bullet point, the things I just talked about? If not, you'll get your chance if I speed up. Okay, that beauty on the right is a segmented blade trap. And what is that? Okay, a trapped ion quantum computer. You take atoms, you strip off an electron, they become charged. They can be trapped by RF, some sort of electrodynamical trap, and then, and so these are this is some sort of Paul trap, I guess. It's not exactly this. I just ripped this off the internet. And then those ions become qubits by looking at. In our case, it's a hyperfine level. It's hyperfine levels that are addressed by some sort of lasers. There, I just completely butchered what a trapped ion quantum computer is. But it's a type of quantum computer that is, I'd say, highly controllable, especially through optics. Optical pulses perform the quantum, the logic operations, single qubit rotations, and I didn't write it. Molmer-Sorensen gates are the native 2-qubit entangling gate for us. I'm going to talk a little bit more about single site addressing, but in the devices, some of the devices out there shuttle ions to different, you call it registers, so that kind of a global beam or an optic laser beam with less focus can be shone on it. Single site addressing without shuttling is going to be possible in the setup I'm talking about. According to what you want in a computing device. These ions they can be measured through a fluorescence, and that's a real ion image from the device on the lower right. Unlike neutral atom devices based on Rydberg atoms, which I've worked a lot with before, ions remain in the trap during measurement. So you collapse the quantum wave function, but you don't blow, like in the Rydberg atom case, you blow the Rydberg atoms out of the traps. They're typically in optical tweezers. In the neutral atom case, in this case, they remain in the trap. All this gets together, all this combines to, I would say, a kind of native clock speed of the device. Like how many shots a second can you get out of these things? And I'd say they're at least 2 orders of magnitude more in terms of data acquisition times than neutral atoms. So anyway, I could ramble forever. I really think these are incredible devices. I really got into just a personal note. I really got into ion traps because of these Hamiltonians. This is a transverse field Ising model and what we call an XXZ model, spin 1/2 models. So as Wojtek mentioned, I'm a condensed matter theorist who studied frustrated magnetism in these models. And I'm a quantum Monte Carlo practitioner by training, and so I became very familiar with the sign problem. And I think it was my PhD advisor. On the right hand side, if I had an antiferromagnetic XXZ model on a triangular lattice, that's something that's computationally intractable for quantum Monte Carlo or even tensor networks or other methods that we work with. And so I remember my advisor saying, you basically have to build that, Hamiltonian in a real device in order to study it. So 20 years later, I'm still on that quest somehow. So I really imagine that, from a condensed matter, frustrated magnetism, many-body system perspective, ions have a potential to realize what I'm calling here quantum advantage and quantum simulation, the idea that we can simulate these types of spin Hamiltonians. I personally am interested in our ion traps for that reason. Hopefully we can build some sort of exotic phases, super solid phases on an XXZ model on a triangular lattice. That's one of my PhD papers there. So that really got me interested. And also all sorts of things like exotic phase transitions, criticality. I just see these things as like, a simulation tool in some sense. But there's, let me skip that. But there's all sorts of other, I guess, philosophies for what these machines could be good for. Another one that I've worked on recently for any of you monitored circuit aficionados is these measurement-induced phase transitions. So, I have a fiducial state, and I have unitaries, which in my case are single qubit and Montmor-Sorensen gates. And then I'm, applying unitaries to prepare some final state. And if they're each one of these is highly entangling, I get something like a volume law in the entanglement entropy.
Jeffrey.
Question?
Yes, there's a question online, sorry, on the chat. Is quantum Monte Carlo just Monte Carlo applied to quantum problems? Or is it a quantum tool to get better solutions for classical problems?
I'm going to read
in
that.
the chat if you want to have a look at that.
It's D+1 dimensional classical Monte Carlo. That's quantum Monte Carlo. It means it's just Monte Carlo applied to quantum problems. I'm not talking about, it's not a, I'm not using quantum hardware to speed up Monte Carlo or to do some different type of Monte Carlo. No. Quantum Monte Carlo means it's based on world line. It's like path integrals. You're sampling all the different path integrals. That's where the sign problem comes in. Certain things are not tractable. That's why that was my point here. Oops. My point here is that I could use an ion trap where quantum Monte Carlo doesn't work. Yeah, keep the questions coming. Thanks for that one. So what I was saying here is if I have a unitary entangling circuit and I throw in measurements, if the measurements have a certain probability, then there's a phase transition in these systems, and the phase transition occurs between volume law and area law entanglement. And so there's some plot that shows a scaling collapse and extraction of critical exponents. I find this fascinating here because in monitored circuits, which I just hopefully convince you can be realized in ion trap hardware, we can realize quantum phase transitions that don't exist in nature. The universality class of this quantum critical point isn't something that you would realize in a material or in matter or in a magnetic system or something like that. I'd say the universality or the universal, the fixed points of the theory in some sense, in these could potentially be different. And so I find this from a basic science standpoint incredibly fascinating. And the idea that we can build hardware in laboratories to realize phases, phase transitions that have never been realized before in nature. I think that's what really floats my boat. Anything else on chat? Okay, no, just the answer. Thanks. I figured it out. Okay, so I'll get back to this, but there's other reasons why I think the device we're building is interesting scientifically. As I started to get into it more and more, and I'll talk about Rajvel and Crystal's work in a minute, I started to realize that, it's not just a matter of an experimentalist handing you an ion trap and then I discover a new quantum phase transition. I mean, there's so many details that go into the control of individual ions and the construction of something like these Hamiltonians or something like these circuits that, I think it's almost impossible to divorce that theoretical idea from the hardware. And in 2018, 2019, I started working with Rajvel here at Waterloo, Rajvel Islam, on some control issues in the ion traps. And I ran into this problem, which is fascinating. If ions are all-to-all connected through their Coulomb interaction, they're stripped of an electron, right? So if you have, these are supposed to be 10 ions that are all connected here. But if I'm smart enough, I can adjust the lasers, the frequencies and the intensities in order to build different interactions. And I've shown a segment of a Kagame lattice. So if I want to do frustrated magnetism, there's my Kagame lattice. And in fact, you can design all sorts of lattices. The problem of going from the interactions, which is these black triangles, that's the JIJs of my, many body equation, from the laser, the Rabi frequencies and the beat note frequencies and the phonon modes, these things are coupled through the phonon modes, is this equation, which has these two sums. It's easy to run the forward problem, given omegas and nus, I can figure out my JIJs. But the control of the ion trap requires the inverse problem. I want to know, I want to know all the laser parameters given the JIJ matrix. This is something that really struck a chord with me because in my field, a lot of people have studied these so-called ill-posed inverse problems, including my advisor's advisor, Ed Janes. And so this has a rich history, this sort of these inverse problems that are part of the control infrastructure. And we first started solving these with machine learning back in 2018, 2017. And so here's a neural network that solves this problem. So I became kind of interested in a lot of the control infrastructure through these unsolved computational or intractable computational problems specific to ion traps. But, you know, it's like peeling an onion. Once you find one intractable control problem, you find a whole bunch. Okay, so that was just my personal story about why I think these are scientifically interesting. Let me look at our hardware now, if there's no more questions on my crackpot many-body physics. Okay, so current state of the hardware. Now, open quantum design. Again, where are they? Crystal and Rajabal, I've been faculty at Waterloo since 2007. I think 2015-ish, Crystal and Rajabal joined. They did their PhDs with Chris Monroe from IonQ fame. And yeah, actually wrote this. Oh yeah, so wrote this seminal paper. So if you want to learn about ion traps, I think this is a great reference that have both Crystal and Rajabal and Chris Monroe on it. They did their postdocs at Marcus Greiner and Misha Lukin's group at Harvard that we collaborate closely with, and then came here again 2015-ish and have been designing their systems ever since. Those again, because of the University of Waterloo perimeter IQC's intellectual property rules, you know, and I'll talk about it in the next section, but we took the intellectual property behind all of our work, the joint work of the labs, and my theoretical and software work, and you know, I guess transferred it to Open Quantum Design, which is a nonprofit that we'll talk about. And this is the core intellectual property that's owned free and clear by Open Quantum Design. So it's a trapped ion designs, which I'll show you. All the real-time control, which is the FPGA control. And I largely work above this real-time box with my students. These things don't mean much to you, but this is the intermediate representations that take, say, circuits or analog, like Hamiltonian pulses or AMO ideas, if you're into AMO stuff, and lower them down into the real-time control. So every one of these arrows is kind of like a compiler. Think of it as a compiler. We also have a suite of back-end emulators. So if I want to simulate my device, you know, some of these like Penny Lane are already open source through Xanadu, Qtip, and some we've written ourselves, TriCal. So this is a combined effort now over the last, you know, I guess almost a decade from me, Crystal and Rajabal. Their contributions, now I'm starting to talk more and more like this is an open source foundation, contribute to the base of that stack, the trapped ion QPUs, quantum processing units, which are delineated into what we call working groups. Those roughly align with two species of ions. One is, you know, this barium 133. Is this the radioactive one or is it 134? I forget. One of these labs, you know, has a radioactive ion. The other one, Bloodstone, is a terbium-171. This is the one I've only worked on myself. And by work on, I mean sitting in the safety of my office. They don't let me into the laboratories. So I'm going to talk mostly about the Bloodstone, the terbium machine. But just keep in mind that we also have a big effort on the barium side of things through Crystal Senko largely. On the left is a chip trap. The barium ion groups have this trap that's been manufactured by Sandia National Lab. But the ytterbium device is 100% manufactured here. It's called a segmented blade trap. And so this is more like the picture I showed you with the ions floating at the edges of these blades. So this is a machine that we're hoping in the control side of things, we'll be able to handle 30 to 50 ions. I'm just going to show you a bunch of pictures now, just for fun. So this is over the last year and a half, 2 years. This is the blades. being assembled and aligned with this rig. And you can see there's 1, 2, 3, 4, 5 voltages and 4 blades. So the ions are, trapped with 20 voltages that have to be applied to this thing. Of course, one of the, what's the limitation for the number of ions that you trap in these types of quantum computer? It's the quality of that blade, those blades, and the alignment, the fabrication quality. It's also the vacuum. Every quantum computer is like a catch-22, right? You have to have either ultra low temperatures, ultra pure materials. In the AMO sense, in the atomic cases, you're suspending, in this case, ions, and you want an ultra pure vacuum. So this vacuum chamber is a major piece of the open quantum design intellectual property. I'll talk more about it. Here we go. It's assembled last year, was pumped out. A year of work went into the vacuum system or more just for this device. It's room temperature. This is a room temperature machine, which means that you have to outgas the chamber and everything that's going to be under vacuum. That's done in one of the labs on North Campus, where we have a clean room and let's see, an oven that goes up to 900. They baked it at 900 degrees Celsius for weeks. Then assembled it under vacuum, pumped it out, achieved what Rajwell believes is world record vacuum, around 10 to the minus 13 millibar, which is, if you know anything about these vacuum systems, it's lower than what the gauge can read. So that's a good sign. This is a picture of the device from January when they first got it into the basement lab with on the optical table, plugged it in, immediately trapped 21 ions. These things weren't qubits yet; they were just ions in the trap, but bode well for, I think, the quality of this vacuum system. On the left-hand side, you see the optics that are starting to be assembled, but I want to emphasize that vacuum chamber, the vacuum system, the blades, and I can show you this online on GitHub. This is all being open source now. This intellectual property, including the CAD designs, has been transferred to OQD, is open sourced. The optical circuit boards, if you want to call them that, which are custom made through a CAD software that was developed in Rajwell Islam's lab. That software has spun out its own for-profit company, but the CAD designs that you see there are included in the Open Quantum Foundation designs. So when you want to replicate that light board, you just download that CAD design, send it to your, sounds so easy, send it to your machinist, and then boom, comes out. So that really, in some sense, is along this, I think, philosophy of reducing the resources required to replicate these devices. And again, one point of the open source, the open sourcing is that we want people to replicate these devices all over the world. That was the hardware. There's an RF system. I didn't talk about the optics much. I don't really know anything about them. There's the vacuum system. It's all part of the lowest part of this tech stack. As you move up into the real-time control, that's importantly the FPGA system. We use an open source FPGA developed, it's called Arctic, and I think it's called the DAX extension, Duke Arctic extension, I guess is what it is. You can purchase these things assembled, or you can build them yourself, but the entire specs are all open source for this, which was important, of the full stack open source. I gotta say, this has been a really interesting for me personally to work on. I was finally able to basically onboard engineers, which I've never done myself as a theorist, obviously. But I onboarded 5 engineers, 3 of them are here, for their 4th year design project. Because this thing was open source, and they built a build server for the FPGA. These are University of Waterloo electrical engineers. So that was amazing to get them, on this project. And of course, it was free, which is amazing for me. But it really convinced me that the way that we handle the intellectual property of this is all working very well. I'm going to skip the software because I'm running out of time, but everything on the left-hand side, digital analog interfaces, these are APIs. We're developing APIs for the time-dependent, like the analog interface. There's lots of interesting work to be done here, but we're kind of doing that last. Get the highest level stuff, the APIs and so on. We'll probably get out more towards the end of this year. if you're an AMO physicist and you want to delve into the light matter interactions, we release these standards. They're in that intermediate representation. Everything is there. You can experiment with your device or our device. Yeah, AMO protocols. We have so lower to atomic. We have a lot of compiler work going on right now. Okay, let me go back now to OQD. That was just current state of our hardware and software. I can show you the GitHub later if you're interested. Okay, so how are we all doing this? OQD launched in February last year, so we're about a year and a bit old. We've got 4 members now from that initial tranche, that initial membership drive. Okay, here they are. Xanadu, very important, University of Waterloo, Unitary Foundation, used to be called Unitary Fund. You might have heard of them. They do a lot of open source work. Haiku is a startup, a compiler in some sense, or a circuit compression. They had a circuit compression intellectual property. They went through CDL and I connected with them. And they're very interesting. So we kind of have, a unicorn with Xanadu. We have a scrappy young startup that's helping with some high-level compilation side of things. We have our university and our Dean of Science and our VP Research that contributed here at Waterloo. We have Unitary Foundation. And those members and any new members we're on board now, it works like this. So again, nonprofit, there's no cap table, there's no shares, there's no ownership. I'll show you a little bit how the governance works. But the members come in, we call them participants in Canada for legal reasons, but in open source foundations, they're called members. They sign a charter, or what we call a participation agreement, but an open source charter is kind of the rules, the guardrails by which we all play in. It includes things like, I don't want to say an NDA, but how the organization would handle the disclosure of its intellectual property. Let me put it that way. The participants, it's an open source community. You can instill your own design philosophies into the computer stack. I mean, not everybody here wants to do study, exotic quantum critical points. That's just me. And I'm only one voice in the organization, right? So participants form working groups around different ideas. You'll notice I didn't talk about error correction. So for example, we have people interested in an error correction, building that as a working group, blah, blah, blah. Participants contribute IP in different ways. So if you have some project you wanted to open source and you think it fits, you can contribute that, I should say, in lieu of fees in some case. So if it's intellectual property that, makes sense, let me put it that way. Participants routinely give that. The intellectual property, there's also employees. We have employees of the foundation. One of the ideas is to, give your students and postdocs a place to land in Canada where they can, contribute to the scaling of our quantum computer here and add their own designs and be gainfully employed. So OQD has employees, and those employees and participants basically interact in the same way. The GitHub, most of this is on GitHub. Our meetings are on Slack, and we have Zoom and so on. We have meetings with certain cadences for different working groups. But GitHub is a mixture of public and private repos. The intention is that the private repositories go public, but they have to do so under proper open sourcing and design cycles and blah blah blah. So we have actually a lot of still private repos that we're still developing. All participants see those repos. So one of the benefits of being a member is that you get to see all the private repos before they go public. Once they're public, they're public. They're public under Apache 2.0 or the CERN hardware license, which is the same permissive type of license. It lets you build software on top of our software. Let me put it that way. And your company can be proprietary, and everything you build on top can be proprietary, and there's no problem with it. So that's the most permissive way, in some sense, to organize licensing. Protected IP, if it turns out to be valuable to certain members or members contribute IP, then we can have licensing agreements back and forth, like RAND licensing and so on. Anyway, that's the boring. I mean, maybe that's boring, but that's the details. a little bit more about the governance. There's a board of directors, so it's a nonprofit. Our CEO is Greg Dick. Very important. I forgot to mention him. Sorry, Greg. Greg Dick was a executive here at Perimeter for 17 years, whose portfolios included outreach, education, and advancement. And he's our full-time CEO. So I convinced him. We poached him from Perimeter to lead the organization forward. And so he's an expert in philanthropy and in nonprofits and so on. And so Greg's really been building out the organization. Like all open source foundations, we have a technical steering committee. Right now, that's me and Crystal and Rajabal, the principal investigators from U Waterloo. And in principle, as we grow, we'll include our own staff, like a CTO and things like that. CTO is important because it connects all the horizontals, which are those working groups I alluded to. And so if you join as a member, you can join an existing working group, or we can talk about a new working group. For example, we have a hardware subsystem working group that I showed you, which is the experimentalist. We have the software mid-stack working group. We have, theoretically, we can imagine quantum error correction working groups, or I don't know, anything you could imagine. If you have critical mass, we can build working groups. We have an education outreach working group. We have a Catalyst compiler working group. So we have a specific working group tied to the Xanadu membership. Because as you know, Xanadu, who's a huge open source advocate with Penny Lane, are developing a new just-in-time compiler, they call it, but it's a compilation stack, which they are plugging into our stack, let me put it that way, through this working group. So this is an interesting model. Again, Xanadu is certainly a well-established for-profit company and so on. We've sort of figured out the model of how we collaborate with them through this Catalyst working group. So it's super exciting. Love to tell you more about that. I guess I won't show you the GitHub repo because that would be extremely nerdy. But there's a large number of private repositories that members get to poke around in, including, which we haven't quite made public yet, the CAD designs for the blade assembly. And so that's kind of the most interesting part. Spec sheets, we spec'd out a couple machines for other people to build. So happy to help with that. This is an education machine that a university was looking at outside of Canada that only wanted to target a smaller number of qubits to make the control infrastructure simpler, the RF control. So this is basically a 10 to 30 qubit version of the Ytterbium device. We plan, as the device that we're building here gets more mature, to start open sourcing the spec sheets. Also, we're basically at the micromotion measurement now, which is important. So as we get micromotion out, as we start to figure out things like coherence times and error models and things like that, that all gets open sourced. Which also I would like to build an open source pipeline. So I'm hoping that actually all of our measurements and all of our data that comes out of the device that's currently in the basement of IQC. And here's our first microwave Rabi flop. So the first qubit that came out a few weeks ago. I'm hoping that we can basically open source all of this data, and which is in some sense to satisfy my other pet project, which is building digital twins from this data. That's a transformer, which I never got time to talk about. But anyway, I have other slides, which I'm happy to share. And I'm going to throw these up here for YouTube. You can pause them. Arguments for open sourcing, membership incentives if you'd like to become a member, and supports for for-profits, which I mentioned. We like to have for-profits either building machines, building the components, building the CAD software. There's all sorts of ways for for-profit initiatives to spin out and to, I guess, support our work and be supported by it. Our first example, we already have one startup, Lightflow. Lightflow launched out of the IQC labs, which I mentioned, which provides CAD software for the designs. And it demonstrates one of the pros of working with an open source consortium is they get to say that their software is used by Open Quantum Design's machine. So, an open source offering in the market, I strongly believe helps for-profit companies demonstrate the efficacy of their offerings. And so just another reason to build out this ecosystem. So yeah, hope you know, that piqued your interest in open quantum design. Of course, there's lots of stuff online. Just look us up. You can see the existing GitHub repos, and I'd say, you know, reach out to me there if you're interested. We have another membership drive going on. We've onboarded at least 2 more members, I think, in the last week, and so we're trying to grow out a second membership tranche. We'd love to have, you know, everyone out of BC involved. So please be in touch, and hopefully I left enough time for questions. So thank you very much for your attention. Ooh, I stopped sharing. Apologies.
Thank you so much, Roger. Any questions? You can unmute yourself or put it in the chat.
I would like to ask one question. So, you know that some quantum technology nowadays is like a sensitive technology, both in national security concern or national interest. So how do you think about how to balance the open source and also that national security?
It's a great question. I actually love that question. I've been thinking about it a lot. So, you know, open sourcing a quantum computer, especially at this early stage, I think there's arguments for making things more secure. And I do look at RISC-V. Now, if you look at RISC-V, you'll notice a lot of manufacturing of RISC-V chips are made in China. But when you get a Chinese RISC-V chip, I believe in principle you know what you're getting. And that's the short version of my argument. Now, RISC-V has a very well-developed silicon root of trust, right? So when you boot up a RISC-V chip, there's a hardware signal that gives you a hashed key that you can trace all the way up through the boot sequence, which makes, in principle, you know, RISC-V chips very secure. So you would know if an eavesdropper is coming in and messing with communications along that boot sequence. And of course, there's always, I mean, it's very nuanced, these types of arguments. But I believe an open source quantum computer, you know, which could be manufactured anywhere, fine, but at least is open source in the sense we know how it behaves, and we can reproduce it and so on, is more secure than, for example, some country who, you know, providing us with a quantum computer that turns out to have, you know, turns out to be marketable. And I don't want to pick on China, but if China builds a quantum computer, like, you know, and we just all purchase that device because it works well, if it's proprietary, I argue that's more of a risk than if, you know, we all build these machines together. So it's kind of like the RISC-V versus the 5G thing. You know, do we want 5G infrastructure? Is it secure? Well, if we had an open source version, I think that we had more control and more transparency on. I argue that I think is more secure. With the caveat that it's interesting because we're in such an early stage of development with quantum computing. So I don't know if that was a good answer. Give me some feedback. Does it make sense?
Great, thank you.
Could you maybe go over the member or participant incentives? Because, you know, I think in practice, I think a lot of us here are, of course, from academic world, and it's, I don't think we're ever throwing a lot of cash around.
Right. This is a little more my pitch to it's maybe my first generation of pitch to members that have a lot of cash. I'm also an academic. I get what you're saying. But I'd say what I didn't really maybe include well here is the idea that if you're, and I think you guys are quantum rich in BC, so maybe it's not as big of a deal for you. But if you were a university or an organization that was interested either in education or in outreach or in training a workforce or in, you know, building your own device, you know, there's an incentive there to become a member. I think first off, it's to get first look at all the designs and so on. You know, in practice, in principle, everything's open source, but there's still a lot of a nuance into how you would align a blade trap, how you pump out your vacuum, and so on. So currently, we've been in discussion with academic institutions about helping build a machine based on these open principles. So again, that would be you could either imagine how it's just like the FPGA. We don't build the FPGA, we purchase it, right? It's open source and it's great. But there is a company in this case that will assemble this and ship it to us. So we're capable of doing that as an open source foundation. We can assemble and ship. I would say especially the most sensitive of the parts of the ion trap. But again, that's maybe just one incentive. I think the idea of education is a big one for us academics. We would love to have a working group that spans Canada to start with, which includes students, right? And what those students would have access to, and students, postdocs, researchers, whoever, would be a bird's eye view of us designing this machine again, but also access to the device in principle. So if we develop the APIs together, number one, develop the scientific incentives. Is this going to be a machine for Roger's crazy projects? Is it going to be error correction? Is it going to be quantum chemistry? Is it going to be something else, right? So I hope I convinced you those high-level design, I guess, directions really influence the software and hardware. And then number two, access. So the open source stack also has an open access interface, through APIs that we're currently developing. And so I think that would be another incentive, to get access to machines. And I think another point is, the engineers really showed me that this is a scalable model for researchers. This is I know it's not a different university, it's in a different department, an engineering department. It was very easy to onboard a group of engineers to make this build server for the FPGA here at the University of Waterloo, because we had an organization where the IP was free and clear, where they could sign a participation or a charter agreement, and it was very clean in that sense. So I could imagine growing this. I believe there's lots of opportunities for what do you call it? The quantum adjacent workforce for developing, engineers, math, CS, all sorts of different fields on this device. So I think there's maybe a slightly different pitch if I'm talking about for-profit, large caps, startups, or academics. I see something on chat. Sorry, I missed before. Do you want me to go through chat real quick, YTech?
Yes, please. Yes, thank you for that answer.
What is the reason behind choosing ion traps? So ion traps are what I like and what Rajmo and Crystal like, and that's what we have our best designs of right now at Waterloo. Okay, so I was very adamant that we focus this stack around some actual hardware. There's a lot of free-floating software out there for quantum computing, right? But I mean, unless it's attached to hardware, and as I go down through, OpenAPL is the open atomic physics layer. As I go through the atomic physics layer into the FPGA, I realized that you can't just fake it at a higher level of the stack. At some point, the hard work of compiling or transpiling or lowering your circuit down into the computer has to be done. And this is, I think, the hardest part. And this is the part where I see the most hard coding or hardwiring. I mean, it's even the idea that I use a Molmer-Sorensen gate is very high up in the digital analog interface almost. The physics behind that is baked down into the atomic physics and the real-time pulses. And you need to connect hardware to build this software stack. That being said, I do want to diversify. I think the first thing we're going to look at is optical tweezers and neutral atoms, which have this similar vacuum systems. They don't have RF control. They would have an optical tweezer, which is another laser, and they might have some other photonics, some different ways of connecting things and so on. But I'm not against at all a solid state like a superconducting qubit. And in fact, the ink's not dry yet, but one of our second round members will be a superconducting quantum circuit startup. And we're actually very interested in the calibration infrastructure. So we're doing these closed calibration loops now. So, okay. So that's my, okay, I'm still reading the chat, but that's my philosophy for starting with ion traps. But in principle, at the bottom of the stack, my dream would be to have all possible hardware, connected at the bottom of the stack. And we'd have different members that specialize in different types of hardware, and different hardware working groups. What's the rough time scale for open sourcing more repositories? We're doing it basically as fast as we can. So the blade trap assembly I would love to get out next week or in a few weeks. It's the CAD file. You can just take that CAD file, and look at how you machine all these things. But we're working on documentation. I don't like just open sourcing random stuff. So the real-time part, the FPGA, the build server, I think is already opened. I gotta look on the repo. But no, all the hardware is being opened, and we're going to connect the analog down to the hardware in an open stack, certainly by the end of 2025. So it's months. Could I further elaborate on what OQD is looking for new working groups or contributions, code design for a specific application of quantum computing? So yeah, I mean, I would love to grow a community. What I'm trying to do is build a network and a community of people. You can dictate the working groups, if you come in as a member. I think it would make sense to start thinking about an error correcting working group. I do need to think about a calibration working group, so automatic calibration protocols. Those are very interesting, and we're talking with 2 new members coming in who have similar calibration problems. So, it's still an experiment, but it's an experiment with, I believe, a robust software stack that's, I think, quickly coming out of it. If I look on the repo, I can tell you how many people are contributing. Oh, I can't see view all. Okay, looks like we have about 30 contributors already on the repository. They're from all different members. Let me put it that way. So yeah, I mean, the philosophical priorities in some sense are up to the members. But I know it has to be done on the hardware, real-time control, compiler level. And as we get higher and higher, I think it gets more and more interesting. There should be lots of opportunities there. I see one more hand, and I'm almost over time. Khaled?
Good question. How do you see all of this sort of apply to the consulting world? I come from Big Four consulting, and a lot of it has been sort of more focused on cyber security. But when it becomes open source, I'd like to get your insights on its application in consulting and business.
So we have talked to people like insurance companies, banks, people like that who are interested in RSA 2048 bit. So let me use that as an example. You have an organization and you want to know when your emails will be hacked by a quantum computer. What do? You hire a consultant, I guess, someone you trust to give you an opinion, or you hire a company that comes in and promises to replace your RSA 2048 with some quantum safe thing, whatever these NIST standards are, so on. But I mean, I think part of the open source philosophy is to give another model for that, how you would interact with quantum technology, because you could see exactly how a quantum computer is being built and the pace at which it's being built and how many qubits it has and how many gates it has and so on. So I think the idea that the specs are public and the roadmap is public and is agreed upon by the members, right? The members in the technical steering committee hopefully release truthful roadmaps that are more or less free of for-profit incentives. And so I think the idea that we have outreach, I call it, but maybe some higher level executive type working groups where people just can keep track of our progress, keep track of our benchmarks, and make their own opinions about timelines based on our technology is one answer to that anyway.
Agreed. Appreciate it.
Thank you.
Perhaps we could take one more question since we're at 3 o'clock, if there were any more. I think we're okay. Yeah.
So we have another question.
Oh, okay, this will be the last question. Go ahead.
Okay, I feel honored here. Hi, Roger.
Hello.
Are you in touch with the people from the Open Super Q or something in Europe? You know, Friedrich Wilhelm Mauch and those? I'm not sure.
I can't quite make out what you're saying. Sorry. Is there a microphone that can
Yeah, I can bring the microphone closer.
get a little closer somehow?
Yeah. Go ahead.
Just tripod, no worries.
Just try.
Are you in touch with the people with the Open Super Q in the EU? Friedrich Wilhelm Mauch and those people in Jülich, I think. I think it might be larger than that.
I didn't catch the name of the organization. Open what?
Open Super Q, I think, is the name of their project.
I'm not sure. I don't doesn't sound familiar, but usually Greg keeps track of everything for me. Open
It's an EU thing.
Super Q. Okay.
Jülich and other folks.
Perfect. Oh, that's part of the flagship. Oh yeah. Okay. I know what you
I
mean, but
believe
thanks
so.
for pointing that out to me.
But yeah, I don't know what's going on there currently. Started a while ago.
There are other open source initiatives certainly out there, and I think CERN also has a community around it, and they're building some open source. Some of it's more software, some of it's different layers of the stack. Yeah, I think I love it. I think this is great progress, and we hope to be Canada's sovereign open source, I guess, offering. But there's no reason why we couldn't be international. Certainly, RISC-V became a very influential international organization with ISAs used everywhere. So I love to see other efforts. Thanks.
Talk soon.
Take care. Thank you. Thanks,
Okay,
Adam.
we probably should close out then. Thanks so much for this talk and for fielding all the questions.
Thanks, Wojtek. It's a pleasure. Feel free to contact me if you have any more questions. Thanks again.
Roger.
Take
Roger,
care,
what's the
everybody.
best way to contact you?
That website, Google Open Quantum Design. There's a form that will filter it so it doesn't end up in my spam email.
Sorry, Google what?
I'll post it in chat. Open.
All right. Awesome. I was trying to look up your LinkedIn, but I couldn't find it.
I don't have LinkedIn.
All right, all right.
Open Quantum Design might, or Greg Dick.
Okay.
But I think we're the only one. Only Open Quantum. Sorry, I can't type and talk at the same time. I know you're waiting.